there are biological neural networks. Please interrupt me generally. So there are biological neural networks and there are artificial, and the question is, what's the difference? Could we reduce this difference, get closer to biological neural networks? And I think that there is very nice, this like a year ago article experiment that they took a million of biological neurons, just connected them to electrodes and trained them to learn to play Pong, and it turned out better than modern reinforcement learning methods. Yeah, so just a million of cells. So it reminds us that they are really great, the biological neurons, and seems quite better, qualitatively superior to our current artificial. And so the question is to try to understand the differences and to build better artificial neurons. So currently there are dominating this multi-layer perceptron and Khan-Kolmogorov network I will talk about. So the one I will talk can be seen as extension of Khan-like networks. So, but they are missing this crucial property. So one property I think is crucial is that animals like rats were found to avoid risk. Yeah, so they do not only seem to not only use value but also the variance to estimate risk. They also need to work on and estimate the probability distribution like higher moment like variance. Yeah, so while currently the MLP scans are rather focused only on value propagation. So the question is how to extend them to also propagate probability distribution, predict probability distribution. Yeah, so this is one direction of extension of standard artificial neural networks. The second big difference, I think, is that if you have axon, it doesn't care if the propagation of spike goes left or right. Yes, it's very symmetric. So there is propagation in both directions, while current artificial are focused on one directional propagation. So I think this is also crucial for biological. So somehow used by evolution. The question is how to also include it in neural networks, so that we train a network and then we would like to put inputs to the outputs and it should still propagate. Yeah, so and the approach I talk about allows in theory for that. Okay, so here is a longer this first slide, so maybe more complicated, but so here is some real neurons. So we can see it's extremely complicated, and as mentioned, there is bidirectional propagation. There are these kind of experiments that they start impulse and read. It doesn't matter if you go left or right. It's quite symmetric system. Yeah, so they have this bidirectional propagation. We can call it there are two-way neural networks. So the name related to a quantum computers I also use. So and there are seems quite superior to artificial. So just increasing the number of neurons seems not sufficient. So that's the current approach. Yeah, just take more neurons data, but many people say that these LLMs is just scaling is dead end like Lacan. So maybe we need some qualitative difference. Yeah, so that's the big question: how to build better neurons to overcome these differences. So there are also approaches with spiking neural networks. Yeah, so trying to simulate it with this propagation of spikes. However, they do it like for 20, 30 years, but I haven't seen many successes. So they say it is more energy efficient, but besides, I haven't had many successes. So generally, I would say that it is too complicated for this kind of approaches. Yeah, so as mentioned, there is propagation in both directions. Then if you meet two spikes, they annihilate each other. Then so with this annihilation especially, it works in bursts. There are many spikes on the go, and the synchronization is extremely important if they meet or not. So there can be a really complicated mathematics hidden inside such neurons. Yeah. So the question is, what is this mathematics? And just trying to directly simulate it with this spiking neural network, I think they are too simplified to properly show the behavior of real neurons. So instead of this very low level, just spikes, I think we should think about a logical neuron. Yeah. So what mathematics is hidden here? Like maybe some matrix multiplication or something. Yeah. So let's not try to go to these single spikes, but think about this one unit and think what mathematical possibilities, properties it could have. Could be hidden by evolution to be helpful for for such biological organism. Yeah, so we'd like to extract mathematics which might be hidden in such logical neuron. Yeah, so like MLP can, but I think they are too simple, and we would like to extend it by properties of these real neurons. In this, basically two ways. That biological has two-way propagation. Yes, if you have a signal, it goes in both directions, and if it can do it, then biology evolution should exploit it. So it might be quite crucial for this processing of information. Then, like I mentioned, rats in experiments not only use the value but also the variance. Yes, so they try to avoid risk. Yes, so if there is some small risk of being dead, then you don't try to use this. So generally, our world is practically probabilistic. Yeah, so we lack a lot of knowledge and should instead work on such probability distributions. Yeah, so in our brains there should be somehow represented this probability distribution of our knowledge about the world. So just working on values is insufficient. We should real biological like neurons should work on the probability distributions. Yes, also we would like to add also this them. Finally, we usually use backpropagation, which is very practical and it's very universal for training. And so if you have a parametrization like here, we can always use backpropagation, but it's not biologically plausible. So I will also explore different training approaches, and I think the most promising is information bottleneck. So I will also talk about it. So generally, I first approach I started like 2018, but it was too abstract. But then there was this explosion of Khan articles, and the one we talk about also can be seen as extension of Khan. So I have written this article, and now I'm trying to update it. So, but generally, the approach is that. What the question is, what single neuron could contain, what kind of information, and in theory it could have joint distribution, model of joint distribution of some local behavior, and having such local model of joint distribution, then we can easily change propagation direction, propagate both values and probability distribution. So this is a very simple and universal approach. So we work on this kind of neurons which hide local joint distribution. Okay, so here are the standard MLP multi-layer perceptron and Kolmogorov-Arnold networks. So you probably well known. So yes, in multi-layer we have just a linear function plus some fixed activation function. And in CAN, they train the function of one variable, originally some B-splines, but we can also use, for example, polynomials. So doing so, it's very similar to what I will talk, but we will extend on, and some summation. Yeah, so we have some very general parametrizations working on the values intended for propagation in one direction, and we just optimize parameters of these huge parametrizations by usually gradient descent. Yeah, so now let's think about trying to improve it. Okay, so here are some qualitative differences between artificial and biological neurons. So especially, as mentioned, like this reinforcement learning, just attaching electrodes, it just learns. While for artificial, we need to prepare everything. Yeah, so they are much more flexible, can tolerate ambiguity. They have integrated processor. They are self-learning. Yeah, so just take a look at impulses and learn. While for artificial, we have to prepare the environment. They are very robust. You can change, remove some part, and they will learn to retrain this part. Then can work in poorly defined, unconstrained environment. Yeah, so there are lots of qualitative differences, and just the current approach everybody does just take more larger LLMs, transformers. So it might be insufficient. There might be qualitative differences. Just taking more neurons will not overcome. Yeah, so and many people now say that LLMs are dead ends, and we need to search for different architectures, different approaches. So. But I will also mention it also can be try to use to improve transformers, like embedding. So, for example, in embedding, we have one parameter is energy for softmax, but maybe instead of one parameter, we should have the probability distribution of some of these, and we could modify the let's say transformer to have multiple. So please unmute and ask. So okay, okay. Uh, So, um, so yeah, uh, so generally we could try to use it to modify standard architecture, like modifying this one parameter standard for softmax, let's say in embedding like transformer, into multiple parameters describing moments, and then together to defining a distribution of this parameter, like h. Yeah, so just one parameter to describe h is insufficient. We need more parameters. So we can also, I think this is also not nice approach to try to improve on standard approaches. Replacing softmax is something better. Okay, so here is some summary of these three differences. Yeah, so MLP cans are optimized for single direction propagation, while neurons are fundamentally multidirectional, also for training. So here we need some long connection for training. Here we only have to use the physically available connections. Yeah. And then we work on values. Why maybe for animals it also valuable to work on probability distributions. Yeah, so we have animal doesn't have full knowledge, can only estimate, let's say, distance from from its house or prey. So I think to to really work to build models of the world, just values are insufficient. We should work also on probability distribution. So try to add possibility to predict, to propagate probability distributions. And here we can do it by grouping a few moments into vector and propagating these vectors. Yes, and then from these let's say 4 vectors, expected value, variance, skewness, kurtosis, we can reconstruct model of probability distribution of given, let's say, distance from some target. Yeah. So finally, we need some different, for especially biological, we need some different propagation, different training approaches. And I mentioned, I think the most promising is this information bottleneck. So in information bottleneck, we think not about the connections, but later about the content of layers. Yeah. So the question is, what should be in this intermediate layer? Yeah. So basically, if it has to predict the next layer, so it should maximize preferably the mutual information. The mutual information is kind of the best generally estimation of bits between one and the second variable. Yes, also information bottleneck, we maximize mutual information between this layer and the next layer. And simultaneously, it's also worth to minimize information about the previous layer, to remove noise, unnecessary information, to compress what is really crucial there. Yeah, so this is local, and I think it's maximizing information and is working on probability distribution. So this approach on probability distribution seems perfect for this kind of training. So here
Can
is
I,
some.
Jarek,
Yes,
can I have a question? Because
sure,
I
sure, sure,
don't
sure. Yes,
under,
please.
yeah, I don't understand one thing, because the main problem of data analysis is that it doesn't matter if you have tabular data or something else, pictures like that. The main problem is that you don't have probability distribution for all your features. So this
Sure,
is the
sure, sure.
reason why you use assumption that features are independent and the rows are independent, etc. So
So
you
you
are
don't
still,
have exact, but you can estimate them. You can see
yeah,
that.
but this
Sure.
is, yeah, but this is assumption that you made for any machine learning and any neural networks model. So you are still on the probability distribution level. Yes, it doesn't matter if so. From data you cannot reconstruct full joint probability
Sure.
distribution.
Always approximate
So
that. Yeah.
yeah, but so what is the, so what is the difference? Because in traditional way, you try, of course, do some tests, statistical tests or something like that to get information about this probability distribution together for all features. But here, how you reconstruct this, and what is the difference? Because
Sure. I talk
you
about it. Sure.
on all on these two approach, you have just probability distribution, and we know that probability distribution is not the basis things, because it's connected
Sure.
with our lack of knowledge. Yes. So
Yes, exactly. Yes.
where is the main point that you do something better than just
So
ordinary?
ordinary are focused on prediction of value. while in practice we don't get prediction value, but later we predict Gaussian, let's say Gaussian value is only the center of this Gaussian. Yeah, so prediction value in practice is for example, center of Gaussian. But
Yeah,
this Gaussian
if you assume that everything is Gaussian, yes, but
sure,
you
sure.
can
Here, yeah, sure. Here I can work on multiple model. Yes, so this is just introduction. Yeah, so I will go to actual models. Sure, in a moment.
okay, so
Sure. But finally, yes, we predict, we propagate multiple moments like expected value, variance, kurtosis, and from them build a model of distribution, conditional distribution, and so on.
yeah, but you see that if you take a characteristic function of the distribution, each moment is you can reconstruct each moment as a first approximation, second approximation at all. Yes, so this is just you start from probability distribution and you take more moments for
Sure. So
the
having infinite number of moments, I could go as close as possible to joint distribution, but in practice I work on like a 4 usually. Yes. So,
yeah, but you still have a classical probability distribution. Yes.
yes, this is classical probabilities. Yes. So the goal is trying to estimate multiple moments, and from these moments estimate the entire conditional distributions.
Okay.
I will talk
So
about it. So this is just introduction. So
okay.
okay, so here is another view. So we have some points, yeah. So like this one, and now I learn joint distribution as polynomial, literally. So from this point, I can find this joint distribution as polynomial, like drawn here, and having this polynomial, now I can propagate, for example, substitute x, this horizontal axis value, and take expected value, and get this plot. Yeah, so this is propagation in one direction trained from these points. But we can also substitute the y, and I get propagation in the second direction. As here as expected value conditional, but it could be entirely probability distribution conditional. Here is for 2 dimensions, here is for 3 dimensions. Yeah, so we just literally build model of joint distribution as polynomial, and then substitute. So let's look at the 2-dimensional case. Yes, so we have just two outputs from the neuron, and we say that the joint distribution is here is a basis. Is convenient to use orthonormal basis, orthonormal polynomials, and our neuron has these Aij parameters. Has a matrix of parameters which describe the joint distribution, like here, and they are moments literally, especially using polynomials. Yes, and assuming this is our joint distribution, from one side, having all the inputs x and y, some points, I can use direct estimation. This is this direct estimation from points of this polynomial. Yes, it turns out that for orthonormal basis, the Aij is just average over this function over the sample. Yes, we have very cheap and simple estimation. I have written many articles on that. Very practical, and you can separately estimate the various moments and then use them to get the model of joint distribution. And beside having this joint distribution model, we can substitute, let's say, y and normalize, and we get propagation of conditional distribution. Yeah, so now based on x, we get a conditional distribution for x based on y. So here we have all the moments, but then we can take expected value. So just the expected value of this, and only the first moment survives. Here's this one. So this Aij is practically are moments. I show further. So if somebody writes, I don't read. So please unmute and talk, because I don't want to interrupt to read the chat. Okay, so here is the expected value using only the first moment, one here. And generally, before this expected value, we have entire density. There are all the indexes. Yeah, so this I index here is the moment of predicted variable. So here is in one direction, so, assuming y, but we can also instead substitute x and get conditional density for y or expected value. And the difference is just the transposition. Yeah, so we have this for two parameters. We have this matrix. For 3, there is the tensor of index 3. For 4, and there are 4 and so on. But we need some simplification further, and we can use it to propagate values or probability distributions in both directions. Yes, very simple formulas, just matrix multiplication. So maybe this neuron could have matrix multiplication. If so, it could work on this kind of representation of the data. Yeah, so very simple mathematics. This is our neuron, and it allows to change the propagation left right. Moreover, it also allows to evaluate the information flow. There is very nice approximation of mutual information as just sum of square of non-trivial moments between the two variables. So it is very nice for monitoring of what's happening there, what is the information flow, for training, information bottleneck training. So very simple approach and very powerful. Yeah, so here is for two neurons, then we can go for two inputs, then we can go to more and build neurons for them. And as we can see, the both variables are from uniform from 0, 1 range. So the best to do it is normalization to quantiles with cumulative distribution functions. So I also talk about it. So our normalization layer is going usually by CDF of, let's say, Gaussian. Okay, so
okay, Jarek, but
yeah.
next question. Sorry for that, because I don't know how to hide Turens. Okay, in this picture you have a nice formula, approximation formula for mutual information. Maybe for me, I think that Fisher information is better way, but okay, but here you have just two variables. Even for iris dataset, you have 4 variables. And for credit scoring model, for example, you can have 500 variables or even 1,000 variables. How good this approximation will be for that
I will talk
case?
about it. Yes, I will talk about it. I mentioned for 3, this way we need 3 indexes and more, so it quickly grows. I will talk about also about it. But we can also do direct, that we directly predict multiple moments and from them build the conditional distribution. So there are various ways to go over it. I will talk about. So this is just introduction still after 30 minutes. Sure, I will talk about it. Okay, so here was my original approach from 2018, very general, too general. So just having a neuron which has some multiple moments and update these moments, and then let's say predict conditional distribution for the remaining. So get some inputs, predict conditional for the remaining. So we could do it. It's extremely powerful, but also abstract. So now I just simplified it to kind of like, yeah. So this kind of approach turns out that like here, this is just trained polynomial of one variable, and for 3 it will be sum of trained polynomials, so it will become. Yeah, so this is nice that especially this formula, this expected value conditional becomes can propagation if we restrict to pairwise dependencies. So we can start with can and slowly add some more properties optionally if needed. Like we could add to can propagation of probability distribution. Like here we could change propagation direction, that we have can. We can change put input to output and propagate in the opposite direction. And also have interpretation of parameter of such can monitor its flow of information as mutual information. And why mutual information? So I'm information theory person, and there the information mutual information is the number of how many bits of information X says about Y, literally. So it is very universal, and it does not change if you permutate variables or apply some monotonous function. So personally, there is only one for me, the best evaluation, mutual information. Okay, so here is this information bottleneck approach by Natalie Tischby and Bialek also. So as mentioned, so here instead of thinking about training about the parameters, we think about the content of layers. Yeah, so if the final layer has, let's say, faces, recognized faces, the first layer has pixels. So the question is, what should be in the intermediate layers? So that's a very difficult question, but generally, this layer should have as much information as possible about the next layer. Yes, should not lose information about what we would like to predict. And so in the original formulation is they use mutual information. Yeah, so that we would like to maximize, choose content such that it maximizes information about the next layer. So this local rule trying to choose the most representative content of layer about the next layer. And simultaneously, they say about that we also need to minimize mutual information with the previous layer. That means that there is a lot of noise in previous layer, and we like to remove this noise. Yeah, so we need to distinguish noise from signal, and this minimization of mutual information in the previous layer removes this noise. Yeah, so they say this is also crucial, and indeed, so I'll talk more about it. So, but the big question is how to estimate this mutual information. So I talk also about a different approach called mainstream approach, Hilbert-Schmidt information criterion. So that's originally for the independence test, that we have two sets. The question is, are they dependent or not? So dependence, so it sounds simple, but it's a very difficult question. Yeah, so we usually think only if you look at correlation, but there are also much more subtle dependencies, and we need to check if all of them are zero, let's say, yes. So I talk about also this Hasik later. Okay, so let me go to, so that was a long introduction, 30-minute introduction. So now let me go to one more concrete stuff. So here is this approach I'm developing for various approach. This I call it HCR as very simple. You can call it polynomial copula. I'll normalize variables to uniform in 0, 1. Then I model the joint distribution as polynomial. That's the basic approach. So it is kind of a world of approaches. I will 20 articles I will talk about maybe briefly about between standard classical statistics, which works on moments also, but it usually use only a few moments as cumulants, which have nice property of being additive. Here we instead we don't care about it being additive. We replace this property to a different property, the property of being able to reconstruct the density, joint density. Yeah, so from moments, there is called moment problem to get the density. It's a difficult problem. So now we give up this additivity of cumulants, and instead there are still moments. There are still expected value of polynomials, but now we can reconstruct the density from these moments. Yes, and in practice we can use large number of them. Yes, so we have these two worlds. One is classical statistics. We have nice estimation, interpretability. We independently can estimate them, uniqueness, accuracy, but we don't have them the density represented. From the other side, we have, and this is very rough description, usually just a few moments. From the other side, we have the machine learning, which has very large descriptions, but don't have any control, and so people often don't trust that. So, for example, financial people don't like neural networks because they cannot trust them, these black boxes. So the goal is to do something between what combines the advantages. Can also work on very large descriptions, but have still the advantages of some classical statistics. Yeah, so working on moment, but such that we say that the density, joint density is just a linear combination in preferably orthonormal basis. Using orthonormal, the estimation is just average over some sampler of given function. So we get still moments. There are not exactly the cumulants, but like cumulant-like moments, but they allow to reconstruct the density. So here is a simple example that for two variables, so we normalize each of them to uniform on 0, 1, as in copula, I will mention also further. And so if there are no dependencies, the joint distribution is 1 on 0, 1 square. Yeah, so this is our normalization. We start here. Then we add this function as f1 as f1. So it says that we go left right. The expected value of the second variable goes up down. So it turns out very close to standard correlation coefficient. Not exactly, but in practice it's very close. Then we have further moments. So here if you go left right, now the variance goes up. Here the variance is larger, the external values, and he's smaller. Yeah, so this is dependence between the first moment of variable and second moment, second variable. and here also, but the opposite. Yeah, so we have now asymmetry in the dependencies. And then this is what financial people call homoscedasticity, dependence between variances. That if one, let's say, stock has large change, the remaining probably have large variance. Yeah, so dependence between variances. So here we automatically decompose the dependencies into these moments and again get the model of joint distribution. Okay, so I have written many articles about it. So for various applications like sociology, finance, astronomy, chemoinformatics, EEG data, so billing analysis, and now I'm trying to go towards neural networks. So, but I briefly mentioned about these applications. This was EEG for as this also by. Okay, so here is some one-dimensional situation that we have the points like here, and you'd like to model them as the density as a polynomial. The degree zero polynomial is constant, it's just normalization. Then we add information about the expected value. So we get this polynomial, then degree 2 polynomial, degree 3 polynomial, degree 4, and so on. So, but going to very high degree, we could do it, but we can see there are some problems. There is some overfitting. There is going below zero, while density can go below zero. Yeah, so this representation of density as linear combination is very nice, but has this problem that sometimes goes below zero. Yeah, in this case, I use usually this, I call it calibration, that I take this density and take, let's say, maximum density and 0, 1, and then I need to normalize it to integrate to 1. Yeah, so if needed, I can do this calibration, but it's costly. It's very difficult. This integration to this normalization is quite costly. So sometimes it's required, but sometimes you can avoid it. Especially for neural networks, I think we can usually avoid it, and the training should optimize it, knowing that there is one. This is one of approximation I'm using. But I usually for neural networks I ignore this problem that this density can go below zero, but we directly don't work with that. But if needed, we can do this, let's say, calibration. Okay, so but the big question is what degree should we choose? So in practice, it is done by cross-validation, that we have separate training and test set and check which polynomial works the best. And in practice, usually the kurtosis is the best choice. Yes, that we work up to kurtosis, especially for financial data, people go there, and for higher moments nobody cares. So there is some arbitrage for up to kurtosis, but further people don't care. So these are usually overfitting. Okay, so here is a very briefly some derivation. So we assume that the density is a linear combination. Yeah. So and we would like to minimize mean square error as integral over distance with the original sample smoothen with Gaussians of width epsilon. With kind of density estimation of width epsilon. So squared. So we get this minimization, and the problem. So we would like to go to this epsilon to 0. That we get this average smearing with Gaussian, but going this limit epsilon to 0, because it is the most sharp description. But the problem is that this term goes to infinity. However, we are not interested in this norm, but only in the parameter. So we can remove this term to find the parameters. So removing this term and using orthonormal basis, we get this formula as I mentioned. That the coefficient is just average over given function. Yes, over the subplot. Yeah, so this is just L2 mean square error, very simple optimization. Estimation of moments. This way we get this is our density as polynomial, let's say. Okay, so as mentioned, it's very convenient to perform the normalization to 0, 1 like in copula. So for this purpose, we go through this cumulative distribution function. Yeah, so if you have a sample from Gaussian, if you go by through CDF of this Gaussian, we get approximately uniform distribution on 0, 1. So the variable, the marginal variable, separate each variable becomes practically approximately its quantile. Yeah, so the one half, then the median becomes 1/2, and so on. Yeah, so this is very simple and natural normalization used usually in copula, for example. So then for such after this normalization, you can perform this representation as in this basis. So here you have points. Here is zero order degree polynomial, just constant. And now we try to use this basis. And here we use much larger basis, up to degree 10, 9. So the question is what to choose, and it's addressed on the next slide. Okay, so here is comparison of this approach with candidate density estimation. Yeah, so the question is, so here are the points. The question is from what joint density they come from. Yeah, so for candidate density estimation, this is the bottom. We put a Gaussian in every point. The question is Gaussian of what radius? So this is this epsilon. So here is small radius. Here is a large radius. And in the propose, instead, we just model as polynomial. Yes, just mean square error estimation of parameters, and we get polynomial of degree 1, 2, 3, 4, up to 6. So the question is, which choice is the best? And for it, we use cross-validation usually. Yes, we have separate training set and test set, and the question is, when can we get the highest evaluation on the test set? And for evaluation, we use log likelihood usually for probability distribution. So just average of logarithm of density over the sample. So here is the evaluation. For candidate density estimation, we get this plot depending on this epsilon. So we can see that it barely goes above 0. And 0 is just assuming 1. So this figure assumption of that density is 1, like here, gives us 0 log likelihood. So we can see that KD barely goes above this trivial baseline, while the polynomials cosines can easily go above, and you can see that the best is this degree 4 polynomial. As I mentioned, usually, especially for financial data, going to up to fourth moment to kurtosis is the best. Then we get some overfitting. So this is the basic heuristic. If you don't know what to use polynomials of order form. That means moments up to kurtosis. So why it works better in cross-validation? Because in candidate density estimation, we assume that the new points will be close to the old points. Yeah, so we put these Gaussians, and the question is if in training set, and the question is if the test set there are near to the old points. Yeah, so it's not very good at generalization. But in this polynomial approach, we just ask for moments, and so there are much better at generalization than just saying that all new points will be close to the old points. Yeah, so it seems much better for generalization to use this global basis versus local basis. Yeah. Okay, so let's think about this basis, and the name I mentioned is hierarchical correlation reconstruction. Yeah, so here for one variable we have this basis of orthonormal polynomials, Legend polynomials. So here you have normalization, constant function. Then we add this expected value, which chooses this linear function. Then variance, which is this one, skewness, kurtosis. So here's for one variable. Now let's go to two variables. Yeah, so for two variables, this is the basis. So here again we have the normalization. The 0, 0 coefficient means constant on both, equals 1. So this is the normalization. Then this row describes marginal distribution of this variable. Then this column describes marginal distribution of this variable. Yeah, so here you have marginal distributions, here and here. Here we have the normalization, and here we have the actual dependencies between them. Yeah, so here are the most interesting for us. Here is approximate correlation coefficient. Here is this homoscedasticity between variances, and so on. Yeah, so here are the dependencies, and mutual information turns out is approximated by some square of this coefficient between them. Yeah, so we can ignore those, only use those between them. So here is for two variables. And for three variables, analogously, again, we have normalization, 0, 0, 0 coefficient. Then we have two zeros and one non-zero. So we have marginal distribution of one variable, second variable, third variable. And for pairwise, we have two non-zero. And for triplewise, we have three non-zero. Yeah, so finally here is triplewise, that it indeed depends on the three variables. that if two variables are large, the delta is larger or smaller. Yeah, so we can conspicuously add. We can start with marginal distributions, conspicuously add marginal distributions, pairwise, triplewise, and go as high as we want. But the problem is that the number goes. So for pairwise go with square of the dimension, for triplewise with third power, and so on. Yeah, so here we need to stop somewhere. Usually people stop at pairwise. Yes, but if needed, we can conspicuously add triplewise. Yeah, so in practice. Yeah, but generally the question is how to choose the basis, the difficult question. So we should use cross-validation to optimize the basis for given problem generally, or use some different approaches. Okay, so here is some high-dimensional situation. So in 3 dimension, we have density again in this basis, in product basis, as product of the three one variable, these legend polynomials shown here. 0 means that there is no dependence, there is constant, and its basic estimation is just average over the sampler of this function. And for more variables, let's say in 9 dimension, if you have all zeros, that means there is no dependence from these variables. So this coefficient would only describe variance between this variable and this variable. Yes, 4th and 8th variable. Yes, so we get this hierarchical decomposition of dependencies. We can first start with normalization, then describe marginal distribution, add information the pairwise, triplewise, as we want. Yeah, so we have full control what we use. Moreover, for example, for missing data, we don't have some variables. We have some rows with missing parts. But if the missing are in the zeros, then we don't care because there is no dependence on this variable. Yeah, so to estimate, to help estimation with this parameter, we only need this curve, and this. Yeah, so we have row only with these two. It is sufficient to help our estimation of this pairwise dependence. Yeah, so we can optimally use missing data this way. And moreover, I mentioned this basic estimation as just average. So this is for static estimation, say stationary estimation, that we have one density, but we can easily modify it into adaptive density. Yes, so for non-stationary. So instead of just saying that all of them have the same contribution, we can say that the contribution drops exponentially with time. So this way you get cheap evolving probability distribution. So not just one density, but in every step it updates with the new points, and we get evolving density can be in 3-dimensional as we want. Yeah, so we can easily add this adaptation, continuous learning, and so on. Okay, so now let's think about this value propagation. Yeah, so that you have this density as this formula as previously. Now we would like to propagate under assumption of y. Yeah, so we just substitute y, and we need to normalize. We need to divide by this integral. So as mentioned, we ignore this density lower than the 0 issue. Yeah, so there will be this problem if you do this calibration, but if we ignore it for neural networks, it seems sufficient. Only when needed, we need to make it positive. So then if we ignore it now, then we get the simple formula as mentioned previously. Yeah, so here is for multiple moments, and then we could take the expected value, and only the first moment will survive. Yeah, so then we would remove the variance skewness kurtosis. So if we want to just propagation of value, we have only this one. Okay, so, and then you could also change the propagation direction by just applying just changing the indexes for two variables. For higher it would be more indexes, but still a matter of permutation of the indexes of the tensor describing our distribution. So here is from one variable, and now let's go to from two variables. Yeah, so we can get this thing, and assuming only pairwise dependencies. Pairwise, that means that at least two are non-zero indexes and one is 0. Yeah, so 0 index means there is no dependence because in our basis there is 1. Yeah, so focusing on your pairwise dependencies, we in fact get only two polynomials. So we get two trained polynomials. So with this exactly come. Yeah, so if we restrict to only pairwise dependencies and to propagation of value, we degenerate to cans. Yeah, so this is our starting point, but we can also conspicuously extend on it. We could add triple-wise if needed. We could also include higher moments to propagate probability distributions. So this is still can be seen as extension of Khan approach. And it needs this normalization. So this is CDF. So, but if it's Gaussian, that means that we need to subtract the expected value, divide by standard deviation, and then use CDF of normalized Gaussian. Yeah, so there is, after standard normalization, there appears this fixed CDF of normalized Gaussian. So it is, to put it into hardware also, it's relatively cheap. Just we need this normalized CDF of Gaussian, let's say. So we can see that yes, this is an extension of Gauss of Kans, and allowing many new possibilities like change of propagation direction in such Kan. Yes, we could. So we have trained Kan. Our parameters are we have interpretation of them. There are moments still. We could now from such Kan we could propagate in the opposite direction. We could extend it to propagate also the higher moments to get also not only expected value but also variance kurtosis. So it allows us to, as we want, to extend Khan in various directions as required for given task. Yes. Okay, so this is one article we have written with Jakub Strava from this A-Inter program, this the previous summer break. So he takes just legend Khan, so some available article library. And it is the basic approach is very similar, but the main difference was that the standard Khan was using just a rescale as normalization. Yeah, so just subtract mean and divide by standard deviation. And here we added this normalized CDF, normalized Gaussian CDF. But just better normalization. So the same, but just better normalization as starting point. And what you can see that now we like to represent the points as a polynomial, preferably a low degree polynomials, because going to higher degree we have overfitting. So low degree is better for generalization. And so this scale is difficult to represent as polynomial. Why? If you do this better normalization to quantize, it's much better, much more appropriate to approximate with polynomial. Yes, and this is seen in evaluation. So here is the CDF cal, let's say. So it can go much better at just degree 4 polynomial. Again, this degree 4, as mentioned, is some universal up to Kurtosis choice. And this is standard one by rescale, and here is our. So we can see that it's better for small degree. Then it goes worse, but it's this overfitting. So the best is using low degree polynomials for generalization, and also much faster at training. Yeah, so this is basic approach. Just take Khan based on polynomials and improve the normalization from rescale to cumulative or empirical distribution function to quantize. And thanks of that, the polynomial representation will work probably better for low degree polynomials. So here is another very simple example, trying to, as in the original Khan article, they show these functions and try to train this function based on here 1000 size sample. Yeah, so we like to learn this function of 4 variables. So here is a joint distribution on 5 variables, also the outcome. So here we literally model the joint distribution on this 5-dimensional cube. And this is the entire direct estimation. Yes, as mentioned, this is just averaging over the sampler. So we need to calculate the basis, and finally this entire estimation is this one. And here is the train function. So it's not exactly because we have also this normalization, but it is this first power minus second power minus third power and fourth power. Yeah, so and this exponent more or less. So it's not perfect, but this super simple estimation could learn this function. Using one neuron, the difficulty is going to have more neurons. Okay, so here is as Sebastian mentioned, there are problems with high dimensions. Yeah, so 5 dimension is large. So again, we need to restrict pairwise, maybe triplewise the dependencies, and there are some problems. The question is to distinguish noise from signal generally. So we would also like to find different approaches, more direct. So instead of modeling joint distribution, maybe directly predict a few moments, and from them model conditional distribution directly. So this is a way to go around these problems, as Sebastian mentioned. So the approach is just to predict multiple moments, like here we use just linear regression to predict the first moment, and completely separately linear regression to predict the second moment. Yeah, performing this kind of optimization, so just learning. So when there is a prediction of value, we can transform it to prediction of a few moments, first moment, second moment, third, and so on. And then getting the polynomials as predicted. So he's first, second, and then here is the final conditional density. Yeah. So here are conditional densities found by prediction of two moments as conditional moments. Yeah. So we can also go in this direction. So to avoid the problems of these high dimensional cubes, by just directly predicting multiple moments and building a conditional density from them, like here. So this is very universal approach, and works nice. I use it for various applications. And for example, some application could be evaluation of variables, this is from SGH, as Sebastian is for. So with Adam Schulz from SGH. Article 2018, I think. So we can evaluate. So this is from some social data. So some tax. So we'd like the original task was to evaluate credibility of tax returns. So if the income was credible or not, based on many variables describing given household, and so here we have the parameters. So we can see that, for example, higher education is positively correlated with expected value. So that means that, but also with variance. Yeah, that higher education is also positively correlated with variance. That means that you can have higher education in, let's say, some philosophy or maybe computer science. So the question is, yes. So there is a large variance. So we can get great interpretation how given factor influences separately all the moments, expected value, variance, skewness, kurtosis, and so on. Yes, and here you can evaluate how many bits you can get if having only this one variable. I call it the relevance. So this is and here is novelty, that if you're having all these variables and removing one of them, how many bits we are losing. Yes, so we can see that there are many variables we have large relevance, so alone are valuable, but they have no novelty. That means that while they have valuable information, this information is already available for the remaining variables. Yes, so the most valuable for us are the novel variables. So something some unique information which cannot be found from the other variables. Yeah, so we can use it, for example, for survey design. Yeah, so if you have a medical patient, and the question is, in his situation, what examination will give us the most information about some crucial problem. Yeah, so I think it's very practical. So we can evaluate how many bits of information each examination will give us. So here is just linear regression, but we could also increase it to, let's say, some neural networks. Yeah, so we can build neural networks that we have some complicated neural networks, and in the last layer we have just usually value prediction, but instead we perform multiple different values prediction as prediction of expected value, as variance, and so on. Yeah, so we just extend it for multiple moments and then build from these moments the conditional distribution. Okay, so here is some summary of HCR articles. So why people usually predict just values. So it's very valuable to also go to higher moments. For example, to also estimate the uncertainty, that just prediction of value, we don't know if it's wide distribution or narrow distribution. So to know how good is our estimation. Then, for example, the distribution can be binomial. So if you have value prediction, we have this value, but we don't even know that it's nonsense. Yeah, so we need the conditional distributions. So data compression is crucial, probability distribution. We have this this contribution of variables like here. Yeah, so how many bits that they carry. We can have better Monte Carlo that we have conditional distribution. So we can beat. So then credibility evaluation, outliers. Then we have this non-stationarity evaluation. So here is this polynomial which evolves in time based on the points. Some Granger I mentioned also further. So improvement of Granger causality and many others, and down these neural networks. Okay, so I mentioned about value propagation, and now the density propagation. So it's more difficult. So now we have this conditional. So now we have x under condition of y and entire density. But for y, instead of just value, we would like to use the entire the density. Yeah. So we have for y we have a vector of moments, and you would like to propagate them through such neuron. Yeah. So it needs some approximation again. So this is like the second or third approximation I use. I call it constant denominator approximation, but it allows us to just say that is linear. That is just multiplication of this b by a and just matrix by vector. Yeah, so we get this kind of formulas, very simple formula. So it allows for very simple way to propagate not only values but entire probability distribution as vector of moments to our networks. And it brings some, for example, some very nice approach, tensor decomposition training that we could, for example, try to start with. We have some this five-dimensional joint distribution as mentioned, and you'd like to automatically decompose it into multiple three variable joint distributions. So this is kind of extension of singular value decomposition into tensors. So we could do it in theory, some this kind of new approach that we just that we have a big tensor and we would like to decompose it into smaller tensor as smaller joint distributions. Okay, so in theory we can do it. I haven't done it, but there are some in this approach we can linearize the entire behavior of the neural network. So we can do here that we have non-linearities only in the input, calculating the function basis. Then we have linear transformation, and then finally, like here, yeah. So just linear transformation, and finally we have again non-linearities at the output. So it's a bit. I'm not saying, but maybe it can be also modified some neural networks and to get also something like that, and hopefully it should learn to work as required if you have proper training. Okay, so this I have shown, yes, for two variables, and this is for three variables, similar formulas. So for three variables, we have this joint density as here. There's this direct estimation, static estimation, then dynamical estimation, expression with average. Then you can have conditional in one direction of density of expected value, or conditional in the opposite direction. And we have this nice, I've shown in the moment, approximation of mutual information. We can perform some optimization of bases and so on. And there are many. The question is how to train the intermediate layers variables. So you could always use backpropagation, treating as just a parameterization. Then you could use this information bottleneck method. Then we can use this tensor decomposition. So there are many additional training approaches. You can always use backpropagation. Okay, so yes, so this is yes. So as mentioned, yes. So direct estimation, update parameters, multidirectional propagation. So propagate and use maybe direct estimation. And I think this I mentioned that it could be used to try to improve the standard architectures like the transformers, let's say. So they usually have this embedding and softmax inside, but softmax has just one parameter like this energy. But if you have let's say in this embedding we have age, yeah, so one parameter is age. So just one parameter to describe age. We don't know this age. We did some probability distribution. So instead we should have some not one parameter, but let's say for moments describing our two moments. So expected value of age and the variance of our knowledge of age of this person, let's say. So here we can do it conspicuously. So just instead of one parameter per let's say age, here we can, let's say, use 4 moments for this age, and replace this unembedding. Instead of softmax, we can use this product of model densities, like log likelihood, maybe some logarithm. Yeah, so, but generally, I think I don't like this softmax. So softmax is using its energy. It's maybe nice, but for probability distribution, it's I think insufficient. We could improve it to actually work with a few moments, and based on them, try to represent, let's say, our knowledge about this embedding parameter like age. Yeah, so I think this is very promising direction to improve current architectures by replacing softmax with a few moments representing the probability distribution. Okay, so again, this information bottleneck. Yeah, so maybe let me. So here is this information bottleneck. Some article. They had these nice pictures that we have this training, and so here is the color is the epoch. So here is full data set, and what you can see that here is the first layer is here. So the first layer goes like here. So what we can see that here is mutual information with the input, and here is with the output. So during training, we increase the information about the output. So yes, we can predict better by going up. But surprisingly, the information about input here it grows, but here it shrinks. Yeah. So this is this compression, they call it. That we need not only to maximize mutual information in the next layer, but we should also minimize with the previous layer. Yeah. So that we should remove unnecessary information from the previous about the previous layer. Yeah. So during further training, it's valuable to remove noise because finally we don't need this noise. Finally, we just need here one bit. So there is much more information. We would like to gradually, layer by layer, remove this unnecessary information to finally live on this one bit. Yeah. So we should do both maximize mutual information in the next layer, but also minimize the previous layer. Okay, so let's go to this estimation of mutual information. Yeah, so here it uses another approximation for practical for neural networks especially. So this is the basic approximation that there is logarithm of 1 plus rho. We just use as rho. Yeah, so we ignore the squares and higher. So maybe it could be done, but it becomes much more complicated. But it's practical, nice approximation. So doing so, our entropy as integral, so this continuous entropy over this integral over this cube, the dimensional cube, is the density times logarithm of density, and we interpret this logarithm of density as one this normalization plus this summation over basis with plus that without this normalization. Yeah, so we get this simple formula that the entropy estimator becomes just sum of square of b plus. That means without the normalization coefficient, without the zero coefficient. Yeah, so here we have the entropy estimator, and we can further go to this mutual information, which becomes sum of square of this plus, which is without zeros. Yeah, so here is the plot analogous to this from Wikipedia. Yeah, so here we have in Wikipedia we have entropy. How many bits of information is in this variable? How many bits of information is in this variable? Then together, then conditional is just this half moon. Yeah, and the conditional is half moon. So we remove this common information, mutual information. Yes, and in these pictures we have these coefficients, and sum of square of these non-trivial between them, if non-zero, is the estimation of mutual information. Yeah, so we can also do the conditional and entropy and so on. Yeah, so we get this very simple estimation of mutual information. So it's kind of similar to this Haskell I will now go to, but much cheaper. So here we can do it with linear size of the sample, while in Haskell you could multiply sample by sample matrices, and so this is like n to third, or so we need this multiplication of sample by sample size matrices. This is very costly. So this is much cheaper and also has better sensitivity. Okay, but we can see also this HCR as kernel-based method. So in HASIC, usually there is city estimation with Gaussian. So in this basis, the difference, the distance between the 2 points are just expected. So we can see that. So here is the smallest distance, the same value, and this looks like this kernel, which is used, for example, in HASIC. But in HCR, you also can use kernel. But this kernel is summation over the number of polynomials we are using, and it looks like this. So there are only positive parts of this kernel. So it becomes diagonal. There are some artifacts, but it's more diagonal than KDE. And moreover, in KDE we have infinite bases. Yeah, so this number of centers is infinite. While here we have finite bases. This number of polynomials we are using. So this is crucial that it allows us to greatly reduce the computational cost. So here we need just the sample size times the size of bases cost, while here we need matrix products of n by n matrix. So it's like n to third, n to 2.5, and so on. So using this finite basis allows and global basis of polynomials allows us to greatly reduce cost, and also behavior is improved. Yeah, so why behavior is improved because here we have this local basis, which is pure generalization, because we say that the new points will be close to the old points, while here we use moments, very, very general description of our data set, which in cross validation gets much better evaluation. So this philosophy of global basis seems much more appropriate for evaluation than this local basis. In this HASIC, Hilbert-Schmidt information criterion, they use this kernel as shown in this kernel, and then they build this. Oh, this is the trace of so we get this kind of just trace of matrix product of two kernels for two samples. Use this approximation of this independence test. How dependent are the vertical and horizontal axes? And for HCR, we also could do it. We can use this kernel like here, but it would increase the cost to this multiplication of this n by n matrices. But we can avoid it. You can just calculate all these moments for this size B number of moments. Each cost us linear with sampler, and get much cheaper and also global basis. So it's much cheaper and uses global basis. And here we performed some evaluation of the information of them. So this independence test. Yeah. So we have some sample. And the question is, are they dependent or not? Let's say vertically horizontal variable, are they dependent or not? So here we start with independent. We independently generate the vertical and horizontal axes. And we introduce dependence here by adding rotation by 0 to 5 degrees. Yeah, so here is relatively large dependence by just rotation. So now we'd like to test that these are independent, these are dependent. Yeah. So in this approach, in this HCR approach, we model them as polynomial. So here is this independent, here is dependent. Yeah. So we can see that. So the big question is how to distinguish that this is noise, this is signal. Yeah, so that's a difficult question, and we need to perform the hypothesis test for that. So here we literally calculate many moments. We calculate standard test is just if they are correlated. So this is for us just one parameter of 16 we calculate here. So we see the correlation is small, or still small, but we can see that this moment is becoming large and this moment becomes large. Yeah, so between first moment of second variable and third moment of second variable. Yeah, so we calculate all these 16 moments, and if they are independent, after normalization, these 16 parameters should be from N01, from normalized Gaussian distribution. Yeah, so we can perform independence tests if these 16 variables are from normal distribution or not. So there are some standard ways like Anderson-Darling, Shapiro-Wolf, yes. So, but they are poor. So I found some better ways. So the best I have found here is just testing the smallest and the largest one. Yeah, so just this violet as the smallest and the red as the largest. Yes, because if there are dependence, this probably is dependence in some direction. So we just need to test this most promising direction. So what we can do, we can compare the values with the smallest of 16 and 0 1 variables. Yeah, so the 16 and 0 1 variables, the smallest of them should have this distribution. You can find it analytical formula, and the largest should have this distribution. And here the actual one was this green line, and here this green line. So we can see that the hypothesis test is gives this integral over these two areas. So here is quite like it can be independent. But now we are introducing this rotation, we can see that this area shrinks. Yeah, so finally the best test I have found is just using these two maximal values, the smallest and largest. And here is then this comparison. So here is this Hasik. So here is independent, here is dependent. Here is probability of being independent based on these tests. Yeah, so we start like 50% that is dependent or not. And then the question is how much it drops after applying this rotation by 5 degrees. So a Hasik drop like 85 times, HCR drops 100,000 times. So it seems much more sensitive. Yeah, so it's much better to distinguish if the sets are dependent or not. Yeah, so it seems better. It's much cheaper. It's linear cost. It's more sensitive based on global basis, which seems more better generalization. And moreover, HCR also the description. We can not only say that is there dependence or not, but this dependence looks like that. Yeah, so it not only shows either they are dependent, but also where is this dependence. So moreover, so here I have also some different approaches. I can also test which of these parameters are seems signals, which are noise. So here are the colorful ones. Here are the probability distribution of the smallest of 16 and 0 1 variables, the second one, the third one, the fourth one, and so on. And we can compare each of them with the actual in given order in our test. And you choose up to some significance level, so getting some models up to chosen significance levels. So we can build models so we can conspicuously distinguish signal from noise here. Yeah, so based on chosen significance level, we also perform some optimization with single value decomposition. There are some randomatics theory, there are some problems, but we can also perform some such optimization of basis. So not just use this standard legend basis, but some optimized one. Okay, so maybe let me at the end go to some slightly related topic, but also neural. So here is some different application of some basic approach, but also I think valuable here. So here is for EEG data that we have two electrodes, let's say FP1 and FP2, some frontal electrons EEG data. Here they are in the same time. Here one is shifted 200 milliseconds later, and here is area. Yeah, so you have we apply two shifts in time. So standard approach would be cross correlation analysis. We will just calculate correlation, how it changes with this delay applied 200 milliseconds plus minus. So this is the orange plot. Yeah, so this is cross correlation analysis. We can see that it's seeing the synchronization. Yes, but it's symmetric while this is visually not symmetric. So let's do it better. Yeah, so instead of just looking at correlation, this is a quite complicated joint distribution, and we can for each delay we can model joint distribution as polynomial. So here is 1, second, third, and so getting this representation that here we have the polynomial parameters, and here is the coefficient for given delta t applied the line. So here you have 100 parameters, let's say, and now you'd like to reduce the number to some, let's say, 4 here. We can use PCA for that, finding the dominant contributions to joint distribution. That we can see that the joint distribution mostly changes in this direction. And here is dependence from delta t, and so it's similar to correlation, but it's much more localized, so it's much better synchronization. So it can be seen as improved correlation coefficient. And the second coefficient sees the asymmetry, that also, so it's much better description. You can find multiple features describing the dependencies. Yeah, so these multi-feature cross-correlation analysis, which has lots of applications. I just find some nuance. So improved of correlation analysis enhancement. For example, for Granger causality. So this is kind of the best way to estimate causality from data. That we have two time series, and the question so we have one time series, and the question is if predicting given value from its past, if you can improve it, having also passed for the second series. If we can, then we can say that it's G causes, Granger causes. If not, we say that it doesn't. So there are some problems with that. For example, there will be a common cause. There could be some area event which cause both. Yeah, so that's the big problem. Generally, but in this approach, I can sometimes I can find it and remove it. So here are some approaches to extend this Granger causality. One approach is to also look at propagation time. Yes, I have these parts of brain and of cortex, and the question is how much time needs to the propagation. Yeah, so we can do it by going to residues, by subtracting from X its prediction from its past, and then look at correlation of this residue versus second sequence shifted by some delta t. So when this correlation is maximal, you can see this is kind of dominating propagation time between Y and X. So this is one approach to also get time dependence, propagation time. But there's also a second one that it needs better this residue, not just subtraction of value prediction, but an entire probability distribution, also variance. So we predict the entire cumulative distribution function and apply it to X. Doing it perfectly, we get IID 001. So if you would do it perfectly, you would completely remove information inside the predicted sequence. Yeah, so now we'd like to ask what if the second sequence can give us some information earlier. Yeah, so first we do this in the beta normalization and then try to find dependencies with the second sequence area. And you can use this approach. Yeah, so one is fully normalized, second is just normalized, and here is for some each data result. So we can see there are multiple types of dependencies. The blue one has maximum like 100 milliseconds. So it will look like direct propagation between these two parts of cortex. Yeah, so directly. Then the orange one has maximum like in 200 milliseconds. So it can be kind of indirect propagation. So that information goes out and somehow goes back to the second part. And moreover, the third one, the green one, you can see often has maximum in 0. And maximum is 0 delta t means it can be also only common cause, yes, because you to require instant communication. So it cannot be communication. It has to be some common cause. So there was some area, for example, some visual stimuli, which causes both here and here, yes. And we are so it allows to conspicuously decompose into various type of causalities. And some of them seem common cause we can remove, for example, or maybe analyze separately. So I think it's a big improvement for extension for Granger causality here for EEG data, but can be also applied for financial data and so on. So to find if there is some dependence between some strange variable and what stock exchange or so on. Okay, so here is this one approach. So we also use it for billing. So 200 points article, so that we could perform Fourier. So yeah, so here we calculate something like that. This multi-feature correlation. Then we don't just apply Fourier analysis. And for billings, it is very nice. So here is state of art for billings. So you like to check if it's proper or not. And here is our. So you can see that the noise is much weaker, and we can see multiple features. And in practice, it looks like it finds spectrum for separate parts of given, let's say, billing. Yeah, so it is complicated situation which has multiple parts which have some slightly different spectrum, and looks like it sees it can separate this into different spectra. Yeah, so I can from one time series I can decompose this mechanical object into multiple parts. So I think it's kind of magic. I don't fully understand, but looks very promising. Okay, so at the end, so maybe some financial, and this is the last slide. So sorry for the longer talk. So okay, for financial again, so non-stationarity analysis. So like we have some stocks like some DAX is German and so on, Dow Jones. And these years 2007, 2008, 2013 year. Yeah. So standard approach is for some so-called contagion. That's how much spreads some between markets, some information is the DCC, dynamical correlation analysis. So it just looks at how the correlation evolves between them. But as mentioned, the dependencies are much more complicated. The entire joint distribution changes. And here we can see that the main change is in this direction, then this direction, and so on. So this is extension of this DCC to multiple complementary and kind of orthogonal directions, and each of them has slightly different dependence. And here are the lines are some important events like fall of Lehman Brothers and so on. And we can see that here we see something that it doesn't see, but here some you see, and they again describe some different type of contagion between stocks. So this is much more sophisticated analysis and can predict maybe some important events maybe before, but later after. Okay, so this is some summary of the approaches. Yes, we can start with can, which are relatively simple, and we can slowly add some more improvements to them in conspicuous way. For example, we can, for given can, we can change propagation direction. Just for trained can, we can give input to the output, and it should propagate back. Like biological neural networks can also propagate in both directions. We can add more possibility to also predict the probability distribution for this can, or maybe propagate probability distributions. We can get interpretation. Its parameters are not some just abstract coefficient. There are actual moments of the variables connected to the given neuron. So as mentioned, can is for pairwise dependencies. We can conspicuously add triple-wise and higher if needed. Then we have this mutual information, so we can have control what are the bit flow through our networks, and better training, information bottleneck, and additional training approaches like direct estimation, tensor decomposition, information bottleneck. So this is one direction, but maybe also we should think about this, just taking current popular architecture like transformers and replace the softmax based embedding with these probability densities by propagating a few moments and building probability distribution of let's say H inside this embedding. So thank you for the attention, and sorry for being long. So maybe one more slide. Sure. Maybe one more
Yes,
slide.
please.
Slightly connect also as Helen has asked us before. So not exactly, but very similar approach, but different normalization. But the task is shape similarity metric, that we have some shape like these digits, and we would like to describe this shape, but without rotation. So practically, it's very important, for example, for chemoinformatics, that we have some chemical molecule. We could just give this shape like positions of atoms, but it would have the rotation. But we would like to remove this rotation information, what is quite difficult. So all shape similarity metrics that we have some scans, medical scans, and the question is if given part is the same but rotated. So we could search for the rotations, but it's quite costly. Instead, maybe we could work on such vector of invariance, rotation invariance, and just compare these two vectors of the two objects. So make it much cheaper. So the basic approach is just PCA. Just make the covariance matrix, and the invariance are traces of powers of this covariance matrix. So if they are equal, then we know that this ellipsoid is the same but just rotated. And so we need to extend it, so we could go from covariance matrix to higher moments, so like 3 or 4, or maybe as talked, but using the Gaussian times polynomial, this Herbig polynomial now, so can represent our shape as polynomial, and then you can find the rotation invariance again. So then for matrix there are these trace of powers, but now we can extend it to higher However, I don't know, this is very interesting and difficult problem, how to get a complete set of invariants. So here we have this all the trace of powers up to degree, how to do it for order tree tensor. So we can build them from graphs that each vertex have this tensor and edge is summation over indexes. But the question is, what set of graphs gives the complete description of tensor modular rotation? So that's a very interesting question, and we can discuss if somebody's interested. Okay, so thank you for the attention, and let's go to discussion.
Okay. Thanks, Jarek. Thanks for this great presentation. And let's see
I hope
if we have questions. Yes, it seems that we have some questions on the chat. So let's start from the first question from George. Which paper is a good survey or reference on the mathematics of Kolmogorov-Arnold networks?
So like 2000s of them. So I'm not following it. Yes. So yes, just put in Scholar Kolmogorov-Arnold network, and you should get I don't know, so like 3000 articles. But I'm not following.
Okay.
But the mathematics is very simple. Yeah. So basic mathematics does you train this one variable function and then make summation, and that's all.
Okay, good. Thanks. There's another question, this time from Ron. BNNs appear to be chaotic and random when compared to ANNs with their rigid matrix tensor structures. And the question is, wait.
Yes, so there is randomness.
Yes, with the rigid matrix. Okay, has there been any work to model their chaotic random nature, and has any modeling been done around the concept of neurons that fire together, wire together?
So this Hebbian rule, I haven't seen it directly applied for training. So generally, the word is for us is probabilistic. We don't know the full knowledge. We can only in practice only estimate probability distribution, like say a distance from something. Yeah. So we cannot say that it's 3 kilometers, but later plus minus something. So we have not only the expected value, the center of Gaussian, but also let's say width is variance. So while the standard MLP cans work on the values, in practice, we need to also work on the probability distributions, and the shown approach can do it. Yeah, so we can literally predict multiple moments, be it from the conditional distribution, propagate and probability distribution as a vectors of moments. So this approach is very general and allows to do it in a conscious way. Yeah, so that. Yes, sure, but yes, there is also chaotic inside, but I haven't started studying it. But generally, then we have a very limited knowledge, and we should be able to work on probability distribution instead of concrete values. Yes, and this approach also do it.
Okay, there's a question on YouTube. What's the main precaution against leaking data?
Against what?
Leaking.
Leaking? I don't know. Linking?
Yes, leak, which means that it's rather about security, probably that we just leak some information is
So I don't know. So this.
Okay. All right. So it was asked on YouTube, so maybe someone can just ask a follow-up question to clarify. There's another question from Ron. Will this BNN inspired work lead to human-like intelligence? And how can this help with reasoning of never before seen problems or through causal inference?
So that's a very difficult question. Yes, but generally, from one side, they say that LLMs are a dead end, like Lekun and many others. Yes, so we need something better. The question is where to go, and so here is some localized differences. Definitely there are true. Yes, so the real axons to traditional propagation. We should try to add to our artificial neural networks. Also, the probability distribution are crucial from various ways, like risk avoidance. Yeah, so definitely we need this two direction to get closer to biological. So this approach allows to get there. But now building real neural networks and large architectures is a very difficult topic. I would gladly collaborate on. But so we have some we have these interns, we have some Discord. If somebody wants, I can invite to this Discord and we collaborate. Sure. But this is the beginning. So This is me, some interns who try to do it, but didn't get very far. So yes, but it's a very big topic. Yeah. How to build finally neural networks, which properties of biological, those if you think something is missing, I will discuss. So what more is missing, and the basic cost is very similar. Yes, this is CAN basically, and just adding extension what is needed. So the question is what is needed, but it gives this possibility to add this extension. Yeah.
Okay. There's another question from Anne this time. Do you think your work would have applicability to analysis of the mold book phenomenon? I'm not sure if you have heard about it. It's a recent recent trend, mold book, where some AI agents. So it's some kind of a social network, social community for AI agents discussing on different topics.
Okay, so I heard about, but this LLMs, but LLMs I know so they only can learn huge data sets. So I don't know. I'm not very optimistic about LLMs, and many people are also that end. So if this is the different architecture, sure, it would be great. But as mentioned, we could modify LLMs, transform this approach. So as mentioned, yes, that we have the softmax and we improve the softmax with multiple moments. Yeah, so this is general approach. Yes, that. So I'm glad you collaborate. If somebody works deeply in transformers, I think this is doable. Yeah, so there is this embedding. Instead of just one parameter like this A, we can have multiple moments, and then this, let's say, an embedding is not softmax, but this multiplication of model densities. So it's complicated, but I think much more powerful. That it has control of probability distribution of each parameter in embedding.
All right. There's another question from Ekamini. Can this BNN be used to model cognitive behavior of learners to assess performance?
So probably in a few years, having teams, it could, but now there is no team, so it needs a lot of more work. But it does improvement over the current approaches. Looks promising, but needs a lot of work. So if somebody would like to collaborate, I'm very open.
All right. Okay, I do not see more questions on the chat, but maybe someone would like to unmute and ask a question.
Sebastian,
I noticed George. He has
Yes.
a question. Which paper is good survey for or reference of the mathematics of CAM networks?
So we've asked it. So Jarek said that. Yes, Jarek, maybe you can repeat your answer.
So there are thousands of articles I'm not really following. So please search for. Yes, please unmute and ask.
Yes, Jordan, please.
Jordan, could you unmute and ask?
Sorry about that.
Yeah, Jordan.
I posted in the chat, and this is what brought this up. This reminded me of a lot of work that's going on right now that I'm hearing about large scale graph processing, knowledge graphs, graph databases, and these big corpuses of information. And this fits exactly in there. And I looked it up real quick and I posted it in the chat. It's based on the system that these Google people did a paper. I think it was like in 2010 or whatever, but they have a whole system for parallel processing, HPC processing for this, but a lot has evolved in that, and there's a big area of this where this can be applied to that area very, very easily. There's solutions here that fits that, but it's a very large, area of research going on, and it's definitely a lot of work, but there's a lot of promise here, and I'm very impressed with this about what you've done.
And extremely general approach. I think it can be used to improve many directions, like this standard embeddings. Yeah, so just where people work with values, I can extend it to work with probability distribution. I can extend it to change propagation direction. So, but it is a lot of work, and now it was mostly solitary work. So I'm very open to collaboration.
Okay,
great,
good, thanks. Do we have?
Satisfied about the answers?
Yes, there's a question from Cayetano, please.
Thank you for your very interesting presentation. I just wonder, I've been thinking about something very simple. Can you hear me? I'm thinking about an insect, an ant. An ant is a very small insect with very small and a very small head.
Yeah.
It has about 50,000 to 1 million neurons, but is highly efficient in terms of organization, movement, and teamwork. I just wonder if the way it operates isn't just probabilistics activity. I'm just wondering if entanglement between the neuron themselves, and if there is entanglement between the neurons, then that may enhance the efficiency. So I just wonder if human neurons and also possibly future computer, if there's some entanglement that could improve. I wonder if your methods in this probabilistic can incorporate also entanglement for the future.
This is generally working on probability distribution. So, like we know rats. I don't know about the ants, but rats are known experimentally that they have risk avoidance. That means that they need also to evaluate variance. Yeah, so as risk. But probably ants also there is some various parameters of environment, and they don't know them exactly, so they should work on probability distribution of these parameters. And this can be mathematically easily done with this kind of approach. So I think the probability is very valuable. So if this Gaussian is wide or narrow, so yes, there will be different decision like for ants. And so it's very beneficial, and we should generally go in this direction. And standard approaches don't do it, and the proposed allows to do it. Yes. So, but I don't know. So yes, so this I know for rats, but I don't know if but yes, extremely complicated. The question is what's happening there. We know that the axons have to do bidirectional propagation, and I believe they should also work on probability distribution, at least to evaluate answer the certainty for risk avoidance. But I don't know the details.
I can help with this answer on this question. That if you mean entanglement in quantum mechanical level, in this approach you don't have something like that because you have joint probability distribution. But this element, like Jarek said about MI, yes, this mutual information is kinds of things that connect nonlinear kinds of interaction or between features and nonlinear correlation. Or this is good, but from basic principle, you know that entanglement is something more than correlation at statistical level. So at this approach, no, there is no any entanglement at this level.
Mutual information is seen as the most basic, so that we literally in communication we send X, it is modified by the channel, the receiver gets Y, and the mutual information is how many bits they can transfer. So that's literally the Shannon error correction theorem. So this is I think the most universal. How much one variable gives bits of information gives about the second variable.
On statistical level.
Yes, yeah, exactly. Thank you both.
All right, thanks.
So maybe can I?
Yes.
Yes.
Okay, so Jarek, it's a very nice approach. I'm very happy to hear about that things, but in my opinion, the first missing is that this is pure statistical framework. It will be very cost on computation in traditional way for a huge systems. So in my opinion, for LLM, it will be not possible to get this information about because this is natural problem in any machine learning, any deep learning. It's doesn't matter how you call it, because it's always statistical frameworks that the main problem is that you don't have information about joint distribution about your problem. Yes, and so this is the reason that we try do everything to get this information from distribution of each feature and correlation between this these elements. So this, but the way that you change your const function to this mutual information is very nice things. But do you? I can try for you one test. You can try analyze very noisy data for that, because very noisy data, your approach will find something that, of course, we will know that this is just noise. So
Yeah, so
this
for
because
example,
this is but this is typically a neural network approach that you don't really care about what is in the data, but you care how to get the to better and better approximation of your in that case it will be joint distribution. Yes, so
yes, yes. So there is very noisy data, but there is some dependence, and I can find this dependence, describe it, use it for some inference. And it is very cheap. This is just linear cost with sample size times the size of basis. So this is extremely cheap in comparison to standard methods.
and this okay, I can agree. In my opinion, this is pure statistical, and you will always stuck on this approach that you approximate your joint distribution. Okay, so the very interesting things, if I can just one remarks, was that in this place that you assume that you cannot take negative elements from raw. It is typical because in quantum of theory you have something like negative elements on your amplitudes. So you see this can be a very important thing that you neglect on this approach. So
So
maybe
I
this.
can repair it. So if needed, I can repair it. I can for neural networks. I think I can ignore it because the training should compensate this approximation. Yes, and that's my way of thinking. But usually I do it. I do it for statistical analysis. I do it. Yes, so yes, for neural networks, there is training to finally got that the final result is good. So it should compensate all these approximations so that the final is
So what you understand but good results?
so good result means like maximizing local equality in cross validation, for example.
So maximization of accuracy of your model. Yes.
Exactly. Yeah. Yeah, so and generally this is you start with CAN and just add possibility to also predict higher moments, conditional distribution from them, propagate them, change propagation direction.
Oh, maybe just one remark for everyone who ask about this CAN neural networks. Just look that you just change basis from X omega like linear basis to functionality basis. Yes. So this is for physicists it should be obvious, and for someone who acts on a XGBoost algorithm is also obvious, but it is cost, of course, more than just trivial linearization in the ordinary multilinear perceptron. So
Yeah, in each neuron the train is one variable function, yes, and there is summation. So usually the original these are B-splines, but can be polynomials. Doing polynomials you get very similar to what I do.
yeah, it can be any from infinity many and uncountable many functions. So you see, but you must choose something. Yes,
Sure.
and the one of the choices is just a linear function.
So linear, we need non-linear later. So because there is only
Yeah, but you see the what is the difference between this CAN and then MLP? Yes, is that in MLP you have one specific choice of your function. If you even look for this formula, you have two formulas, yes, and if you change this phi from x to x omega or w is the same. Yes. So this is just specific choice of CAN networks. Yes.
So this is some guess parameterization, and you just gradient descent.
Exactly.
So and the proposed approach allows to see this parameterization as actual as hidden joint distribution in each neuron with non-parameters with controlled information flow in bits and extension to higher moments and change to the propagation direction. So this is CAN still, but with possibilities of many improvements, extensions. So this is more than just so now this is just parameterization here, but in the view of presented, it's later this is a model of joint distribution already inside that such CAN. For example, for CAN restricted to only pairwise dependencies inside neurons, and yes, and unidirectional propagation. So we have so from input we have many moments, but from output we have only first moment. But so it gives better interpretation of the CAN and control of information flow.
Yeah, but how with computation time? Yes, because it's if you put something not linear for that, it is not obvious that it can be faster or not faster from linear multi-layer perceptrons.
So if you use polynomial, then you can see it as this presented approach.
Yeah, so if you use polynomial, it means that I can change my feature for polynomial's features. Yes, I can put x i x j new feature and put this to the multi-layer perceptron. I have the same on this second level. I have the same results.
Yes, there are literally moments in view of so so here you have expected value. So we have model of joint distribution described by moments. A, I, J are moments. Then you find the formula for expected value and restricting to pairwise dependencies. You can sum of trained polynomials. You get CAN. But in this view, your coefficients are still moments of the three variables. So literally this A1, J0 is dependence between the first moment of first variable and jth moment of second variable. So we have
this is not full joint distribution.
it's
Just approximation of three variables by two variables dependencies. So
yes, so this yes. So CAN can be viewed as I mentioned that as approximation of distribution of pairwise. Yes. So here we can use it this way, but we have interpretation, and you can also conspicuously ask triple-wise, no problem.
Okay, to end, Jarek, I will contact with you because I will try show you some more general foundation of this approach. Okay.
Sure.
All right, thanks. There is
Okay.
another question. Is this science and analysis useful to understanding the operation of biocomputers? And there is information about the 16 lab-grown brains run world's first living computer in Switzerland.
Yes, so this was this first slide. Yes, that's a million of neurons. So this article. So generally, the goal here is to catch up with biological. Yeah, so to find what are the weaknesses of current artificial and to like these two base difference that unidirectional propagation and also of probability distribution, and try to build artificial which are closer. Hopefully, finally, in few years, maybe build artificial which are close to biological in the possibilities. That's the goal,
Right.
but it had goal and requiring some collaboration.
Okay, thanks. Do we have more questions to Jarek? We are reaching the end of the meetup, but maybe there are some last questions to ask.
If somebody's interested, we have some Discord. I could invite. So
Yeah.
please.
If you want, Jarek, you can share some links here on the chat, or I'm not sure if you have slides with the links.
Discord. Okay, so I sent a link to Discord of our group, the chat. So this is for two-way quantum computers originally, but then there was an intern program. So and there was added one of the topics was this biology inspired neural networks.
All right.
Okay, where is the chat? Okay, copy and chat. Okay, let's see the chat. Okay, where is it? Oh, yes, there is chat. Yes, there is chat. Okay, so here is our Discord. If somebody would like to, we can join and collaborate. So there are some interns. We have some two articles written. The interns of the two articles, if interns were. One was this can with polynomials, yes, with Jakub Strava. So to change from can with polynomial, the basic approach is just to replace the rescale with better normalization to quantize, also adding this cumulative distribution function, and it provides better generalization thanks to more uniform distribution. So this is one article. And the second article, if interns were this one, so but they did not know much. So to compare with the state of art Hasse Hilbert information criteria, that we get both better sensitivity and much cheaper and description, so it's much better alternative for this state of art Hasse.
Okay. Thanks. All right, so I think that's all for today. So thanks, Jarek. Thank you once again for the great presentation and answering all the questions. There is a comment from Mike that the application to Discord is awaiting review, so I believe that you will accept it.
So I accept the moment.
Yes, thanks everyone for coming and for asking all these interesting questions, for participating in this meeting actively and discussions, and we hope to see you on our next events, next meetups. So Ron has just commented that Helen is the best, and I think that we agree. So Helen, thank you as well for organizing this meetup. And I think we can finish for today. Thanks everyone.
Okay,
Have a good week. See you next time.
Thanks.
See you. Bye.
Bye. Thanks. See you.
Okay. Bye-bye. Thank you.
Okay.
Bye-bye.
My eyes.